event is organized in collaboration with our event partner Marposs and co-sponsor Zeiss India. The webinar is focused on understanding the nuances of cell making, quality control, as well as the situation with the raw material access and the possibilities for India. So let me go through the agenda and introduce our expert speakers for today. We will start with an introduction to lithium-ion cells by Mr. Rahul Bollini, who is a cell R&D expert with JLNPhenix Energy. Rahul also played an integral part in putting together this event. So thank you, Rahul, for joining us today.
You're welcome.
Thanks, Rahul. Next, we'll get a sneak peek into the market for lithium-ion cells, supply chain, and how India is positioned at the moment. The presentation will be made by Mr. Preetesh Singh, who's a specialist case and alternate powertrains at Nomura Research Institute. Thank you for making time for this, Preetesh.
Thank you.
We'll then go on to understand the basics of lithium-ion cell manufacturing process with Rahul Bollini. And next we have Mr. Franco Stanghellini, EV Industry Manager at Marposs, who will be making a presentation on testing operations in lithium-ion cell manufacturing. Thank you for joining us today, Franco.
You're welcome. Franco is okay because Stanghellini is definitely too difficult to spell.
Yes, Franco is easy. Thank you for that. And this will be followed by a talk on X-ray solutions for quality control in cell manufacturing by Mr. Manoj K S, who is the Head of Business Development at Zeiss India. Thank you, Manoj. Very pleased to have you here.
Thank you, Priyakshu. Thank you for the opportunity. Thanks.
Thank you so much to all the audience members and the experts for making time for this event. After the presentations, we will have a Q&A session. During the session, anytime the audience can put their questions in the Q&A box. The panelists will have the option to answer the questions by typing their responses, and select questions will be taken up during the last 20 minutes of the webinar, which are marked for the Q&A session. So without any ado, let me request Mr. Rahul to share his screen and start his presentation on the introduction to lithium-ion cells. Over to you, Rahul.
Thank you, Priyakshu. I hope my screen is visible.
Yes, Rahul, please go ahead.
So, introduction to lithium-ion cells. Working principle of a lithium-ion cell. So basically, a cell is a battery where lithium-ion cell is a type of battery where lithium ions move from cathode to anode during charging, and they come back from anode to cathode during discharging. So this is the basic principle of a lithium-ion cell. During this process, electrons are released from the anode to supply energy to the application during the discharge process. A rapid shift towards lithium-ion battery. They have become the ideal choice because of the following reasons: high energy density, fast charging, it has no memory effect, and low self-discharge. So, comparison of lithium-ion battery with lead acid. So, suppose if we talk with respect to lead acid batteries, which were dominating the electric vehicles market, especially the two-wheeler, three-wheeler, why is lithium-ion battery overtaking lead acid battery? So these are the main reasons: high gravimetric energy density, which is the watt-hour per kg; volumetric energy density, which is the watt-hour per liter; the charging speed, which is the C rate of charging a battery, the charging time of a battery. So lead acid traditionally used to take 6 to 10 hours all the way. And lithium-ion batteries can be fast charged, really fast. This is also possible. Discharging power, which is basically, the power output. Suppose you have all these premium scooters these days who give you 90, 100 km/h speed. So that is possible only because of lithium-ion battery. And the round trip efficiency, lithium-ion battery is much above 90%. And lead acid battery, they tend to be 80 or below 80 sometimes, depending on the C rating of the battery, and partial SOC. So this was a major issue with lead acid battery. The partial SOC is basically when you are using the battery further after it is being discharged. Suppose you discharge up to certain level, and then you're supposed to charge back the battery if you're using it again, which is a very common scenario in electric vehicles. So the batteries used to lose their capacity to hold the life and all used to come down. So that's no problem in lithium-ion batteries. In fact, you can see your cell phone. You can use and stop using at some certain point and then continue using it all the way to zero. Not a problem. Various chemistries of lithium-ion cells. So LCO, which is the one which was commercialized by Sony in 1991, and even today it is there. So almost 31 years, it's still there. And it is used in our cell phone and all the portable electronics today. NMC, which is quite popular in two-wheeler today, and because of their high energy density and volumetric and gravimetric. NCA, this is for even higher volumetric and gravimetric energy density. But NCA comes with a cost. Their ability to experience thermal runaway is much before an NMC. So only with careful thermal management, NCA is recommended. So very, very premium companies only consider this someone who has very high budget and they're running out of space. So they can spend money on thermal management and all. Yes, LFP, this is the India's choice, cheap, uh, reliable, lasts long, durable, safe, you name it, it has everything. But it comes at a small price. I don't blame LFP actually. That's the law of electrochemistry. When batteries get heavier and they occupy more space, that is when the battery can be more stable. So that's why people generally ask me, how is NMC or LFP compared and all. Obviously, NMC is lighter and it's less bulky kind of thing. But yes, the stability issue will be there. Its ability to catch fire is much, much earlier compared to LFP. And its life is also less. Fast charging ability can also be, again, looked at because the heat and all needs to be controlled. And then LMO is also very old technology. Nissan Leaf was using it. And there were some failures and all. Now there's a new formula, NMC plus LMO, which is again gaining good popularity. LNO, this never really took off. Saft was doing some time ago. And Johnson Matthey also tried, didn't really take off. And LNMO is again a new kind of thing where it's basically LMO, added with nickel. So there are various popular things, how it is divided, 0.5, 1.5, there are various ratios. This is gaining good because it has no cobalt. And its voltage is really high. It's 4.9 full charge, 4.95, depending on the electrolyte. LMFP is again, Tesla has been recently talking about this. They are talking to CATL regarding this. So this is a modified version of LFP, where manganese is doped to achieve higher voltage. So voltage can go all the way to 4.1 full charge, as opposed to 3.65 in LFP. Various form factors of lithium-ion cells. I'm sure you might have seen cylindrical, very, very popular. Pouch is just gaining traction in the market, but it has very heavy, very high potential. Prismatic, predominantly used in three-wheelers. And yeah, so let's talk more about history of lithium-ion cells. Lithium-ion cells was first commercialized by Sony in 1991. It was LCO chemistry. Its form factor was 18650 to be fit in digital cameras. Later on, pouch cells came into effect for portable electronics such as cell phones. So today what we use is pouch. Some of the smaller phones have even prismatic with a metal casing. The low-cost cell phones you might have seen. Yeah, popular cell chemistry in India. So with respect to our countries, how it goes, LCO, like I said, cell phone, it's all LCO. NMC two-wheeler has been predominantly looking at it, but lately because of fires and all, people are thinking all the way they want to go to LFP. They are working on modifying their vehicle chassis to accommodate the little bit bulkier LFP, but they feel this is the way to go. And LFP generally a predominant market in three-wheeler because of its price and all. So, but as of today, NMC is doing very good in electric vehicles, especially two-wheelers. LFP is preferred in low range where the volume of the battery is not a problem. So low range, if you see low speed vehicles, you would probably see 24 Ah pack made using 6 Ah cells, 4 cells in parallel. And energy storage, you might have seen solar or any kind of energy storage, you will see a lot of LFP. And NMC cells in its application, like I said, it's not so stable, and but advantage being it takes up less space, it's lighter also. long range two-wheeler, long range four-wheelers. So if you see Hyundai Kona, they use NMC. Two-wheeler, all the premium companies as of today, they are using NMC. LFP three-wheelers, like I said, predominantly, and electric buses also. Because of it's more of a durable product, so where buses can have a lot of wear and tear and a lot of movement and a lot of ruggedness is required, so LFP got you covered there. And LFP is gaining a lot of popularity in two-wheeler lately because of a lot of amendments from government regarding the thermal propagation and all that is being talked about in AS 156, where the batteries must be able to have that fire when you send it all the way to 300 degrees Celsius of heat is being given to the battery, what happens to the rest of the battery. So a lot of questions regarding that, so LFP is taking an edge over there, but still people are looking at that. And four-wheeler, lately Tesla has been buying a lot of LFP. In fact, 50% of the vehicles that were used by Tesla, recent survey said, and especially in China and hotter countries. So I'm assuming when Tesla comes to India also, they'll be probably using LFP only. So because of Tesla demanding so much of LFP price has also slightly gone high. And the demand of lithium carbonate, which goes in LFP, that is also shooting up, and it has been really high. I think Preetesh will talk about that. So understanding the cell parameters, cell capacity in EH, cell nominal voltage in volts, V, and cell over voltage, cell under voltage, cell IR, SOC, SOH, gravimetric energy density, volumetric energy density, end of life, second life usage. So we'll be covering all this topic one by one. How to measure cell capacitors? This is a typical charging channel which you will see, and I highly recommend whenever you buy a battery or something, this must be used. All your cells must be actually graded based on capacity. It's very, very important. If the capacity grading is not done, then your pack will have all these balancing issues. Yeah, so especially the cells which have lower capacity, they tend to reach the over voltage fast, and the BMS cuts off, and the charging of the rest of the cells have those issues. Anyways, so this is the grading machine where when you get a new cell, you charge, discharge, and then charge to a certain SOC to see the OCV and IR, and then you take on the further thing. Obviously, you get to know the capacity also. And the popular cell capacities used in India. So these are all pretty much you can see in the market in NMC. Cylindrical, this is more with respect to what's moving in the market. Cylindrical 2.2 is very common in toys and solar, some of the lightweight solar application. 2.6 is the most dominant in two-wheeler, very proven also. It uses NMC 532 cathode material. And NMC cylindrical 2.9 is gaining a lot of popularity lately because for the same weight and the same volume, we are getting 11.5% more energy. So 2.6 giving you 2.9. So that's a wonderful thing. So people are looking at that as well. But it comes with a little bit of stability here and there because that is probably using NMC 622. But and NMC cylindrical again, the 21700, there is one 4000 mAh in 21700 format. 4500, 4800, 5000. So 5000 is the last, and anything above 5000 is not there as of today in 21700. And there's one more 5000 mAh in 26650 as well. And coming back to LFP cylindrical 3.6 AH 3.8 and 4000 mAh, these are all something in 26650 or 26700. Then 6000 mAh, very popular, probably the most demanded LFP cylindrical cell in 32700 format. And LFP prismatic 80, it is kind of getting out of date now. Maybe the end of this year or next year, it will be completely out of the market. 86 is very, very popular in e-rickshaw. So somebody who doesn't want all the way 100 AH can actually go for 86. 100 is the highest demanded prismatic LFP cell. So moving on to, so let's talk about all the parameters one by one. Cell IR. There are two methods to test. There is ACIR, DCIR. ACIR is pretty much what all the sorting machines fitted with famous systems like Hioki or Chroma and all those systems. They use this ACIR method where 1000 hertz is passed. And then let's quickly go to DCIR. DCIR is more of a serious test, which not everybody uses. It is more of something which the cell manufacturers take care of it for you. And generally DCIR value is, I would say, maybe approximately about 2x of the value of ACIR. It's on the higher side. So in this, basically, it measures the ohmic resistance of the cells, cell's components, and high DC current is passed to check that. So that is what it is. Yeah. How to measure OCV and IR? This is pretty much the sorting machine, which is very popularly used by many battery pack manufacturers. So after the cell capacity is graded and OCV/IR is done, and then you take it for welding, as integrating the cells in series and parallel combination, and then you add the BMS. So that's pretty much the pack thing. Nominal voltage, over voltage, under voltage. So nominal voltage is the average voltage delivered by the cell for a particular depth of discharge, for a particular C rate, at a particular temperature. It's a very wide and very the subject which depends on a lot of variables actually. But pretty much whenever we take the values LFP, we take 3.2, NMC sometimes 3.6, all the way to 3.7. Again, like I said, the factors come into play. And what is over voltage? It's the voltage where the cell needs to cut off. It shouldn't charge anything above that. So the question is why? After that, the electrolyte becomes unstable. It can lead to decomposition. So these are all the values generally set by the manufacturer. And over voltage for LFP is 3.65, for NMC is 4.2. I think I put it the other way. Fine. And under voltage is where the cell must cut off at a lower depth of at a lower SOC, because that's when after that, pretty much if you see the graph, the voltage dips like anything and you don't get much of the energy output. So that's why the manufacturers say, okay, this is something you need to cut it off. And if you discharge even further that, it can lead to bulging or swelling of the cells, which is not good. Irreversible capacity fade is huge. So for LFP, it is 2.5, sometimes 2.2, some of them write even 2.0, depends on the manufacturer. But I highly say sometimes you have to get your own thing also, where you could look at the graph and wherever the voltage just dips, you could probably cut off over there. And for NMC, it is for 2.75. I think I put it wrong. Okay, fine. So coming to SOC, state of charge, this is a topic of great interest. A lot of R&D is going on because, to be frank, today, whatever SOC your vehicle shows, it's probably not very accurate. Everybody knows that. And there's a big race, a lot of R&D, a lot of things are going. Many companies, OEMs, electric vehicle OEMs, they are working on a lot of algorithms and all these things to be able to accurately measure this. So basically, if you see low cost solutions today, or any kind of solutions, low cost, they probably use OCV based SOC, where it's basically called direct measurement, where they look at the corresponding voltage of the cell and they predict SOC, which can be a little bit inaccurate, especially with flat curve LFP. And with the smart BMS coming into the picture, that is going to be a thing of the past, because smart BMS, you can have bookkeeping method, which is probably the Coulomb counting, where you could actually see how much of amps is going discharging from the battery and for what period of time. And every 10 or 15 days, you're doing one full charge to see the SOH. And there's a lot of things that are taken care of. So that is going forward, that problem is completely solved. In fact, we were doing some tests in JLNPhenix also regarding the SOC. Now, I don't think it's a problem at all. So, but SOCs basically tells you the how much energy in the battery is left. And it can basically, it is something which is required to, so that even the electric vehicle user. In fact, I got my scooter recently, so I look at it. Yes, range anxiety is true, but I look at it and yeah, okay, the SOC is so and so, percentage is so and so. I need to get home. I prefer home charging, by the way. But yes, SOC plays a vital role, and I see sometimes it is little bit fluctuating and all that. I can understand there are some issues with that. It's a new industry. Everybody's trying really hard, but yes, with smart BMS, that should be taken care of. And types of measurement, I just spoke about direct measurement, bookkeeping methods, and high accuracy estimation is a very complex. So in fact, some people are working on hybrid methods where the direct measurement and bookkeeping together, where the data can be overlapped for accuracy. But this is something, a very great R&D. If someone is from R&D field looking in this particular field, I would highly encourage working on this field. And importance of SOC, it plays a vital role during discharging to understand when the battery, like I just told. And in UPS, home ESS, or any kind of ESS, you need to understand. SOC will probably tell you, okay, this much of output can be left, or how this much of energy is there. So at this particular power, as state of power, there's again There are other terms also. State of power is something very popular in UPS, where it talks about, okay, at this particular power, you get this much of backup and all that. So that is the importance of SOC. And SOH is basically directly linked to the life of the battery. So SOH is called retention capacity. It is inversely proportional to the irreversible capacity fade, how that go, how, or you can say directly linked also. But the whole idea is, as the irreversible capacity fade is on the higher side, and uh, so as the irreversible capacity fade happens, the SOH keeps dropping. So that is the relation between that. And why is it important? Because a particular range is expected from an electric vehicle, or a particular backup time is expected from a ESS, which will not be the case with battery aging or with SOH coming down. So SOH plays a vital role. Again, like I told in bookkeeping method also, this is one of the parameter which is taken in consideration for the algorithm. And it is we've coming to importance of SOH, like I just told. And why, another reason why it's important is there is an end of life which is defined for basically batteries. Say sometimes if you look at an iPhone, you get a alert if it SOH as its battery health has reached 80%. It says, please change your battery. So in cars it's all the way to 70%. Again, depends on chemistry at the form factor, the capacity, but generally it's 70%. You can use up to 70. Some say 80, depends. Again, you can talk to your cell manufacturer regarding that. So when it reaches there, the battery is not fit to be used for especially EV application. Definitely not. We'll talk more about that in the second life batteries. Gravimetric energy density. This is the one of the reason why NMC is a little bit preferred. So this is pretty much the formula where the answer comes in watt-hour per kg. If you take a 2.6 AH today, it would be 48 grams. It comes about 199 watt-hour per kg. And if you take a 6 AH cell, it comes about 143, 145 watt-hour per kg in LFP. So that is one of the reasons for someone who wants lightweight, they go to NMC. But to be frank, that 50 grams is going to cost you in the future when all this battery life is less and you're overpaying for it. And if you actually look at the graph, to be frank, LFP would degrade slow and NMC would probably dip like fast. So you're overpaying and your life is less, and the range per cycle also is just dipping. But anyways, coming to this is the reason why NMC is preferred. And I was just taking, so if you take 3.7 volt, it comes about 205. If you take 3.6, it comes to 199. So this is a 47 gram cell of 2.6 AH, very, very popularly used in EVs today. And volumetric energy density, this is also one of the reasons why NMC is preferred, because it takes up less volume. And let's see the example. It comes about 583. If you take 3.7, it comes about 566. If you take 3.6 volt nominal, depends on your cell manufacturer. And if you take LFP 6AH, it comes about 341, around something like that. Yeah. So end of life, this is again another interesting topic where again, the OEM needs to educate its customer that when your battery life is when the range has come down to so and so level, you should be able to replace the battery, because it's not safe. Sometimes it's sometimes you might have seen people use 5 years old or 6 years old phone, and they say, yes, I get a 2 hours of backup, I can recharge again and again, but actually saying it's not safe, and your batteries would have bulged, and you're looking at safety dangers, to be very frank. Especially cell phone batteries, LCO is the most unsafe chemistry in lithium-ion, literally the unsafe. There cannot be anything else more unsafe than that. Yes, of course, NCA is also unsafe, but in Indian point of view, so it is always recommended that you sometimes ask, whenever you buy electric vehicle, you ask your manufacturer that, or your dealer or supplier or anybody, that when do I go for a battery replacement? Till when is it safe to use my batteries? Especially when you're buying NMC and CA batteries. Yeah. And the question is, why are we supposed to change? One of them is your range is really low. or backup time in ESS is low. Second thing is the charging speed. You cannot charge really fast at that particular time because the internal resistance of the cell would have also increased. With aging, it's a factor of lithium-ion cell where the internal resistance of the cell increases. It goes all the way to 1.5x of earlier. So the heat generation is also 1.5x. Output power also, you don't get that kind of output, which is not good. You will not get the achieved speeds, or you will not get the load that you want out of your ESS. So how is UL decided? So there is, like I told, there's IR and then the retention capacity. And IR is pretty much up to 1.5x, like I told. That is the thumb rule, but it can, again, it's better you verify with your supplier. Retention capacity, like I said, 70. Some of them claim, some of them 80. You can talk to your supplier, not a problem. For example, Tesla says this battery need to be replaced when the battery has degraded to 70% of original capacity. Some companies set it 80 also, like I said. The terminology is called end of life in EV application. The new regulation Indian government, by Indian government, mandates that vehicles must have inbuilt tracking system with batteries, SOH or health to notify the battery has become unfit. So there will be a lot of SOH that will be displayed. SOH will be tracked and displayed, and it'll probably show you that it's unfit, or probably the dealer would have told you that, okay, when you see 70, you change the battery, something like that. But government is taking this very seriously. Usage of batteries beyond end of life. So that is where the second life usage comes into play. And if you still want to use beyond that in EV, then the battery simply heats up, and the temperature, the thermistor, the temperature sensor of the BMS will simply cut off the pack because the battery simply heats up. So you'll have to probably redesign the BMS, which is not a good idea, by the way. And constant cutoffs, and and the charging hours will be long for that particular range, and it's pretty much not worth it. And you're looking at thermal runaway, especially NMC, NCA, and because the aging is done, and the manufacturer is told clearly not to use beyond that, and you're still taking a risk. So this, again, we need to educate. If any of you are OEM, you need to educate your customers. Second life usage, second life, again, the retired batteries come back, they're dismantled, and then cells are graded like they are brand new cells for capacity, IR, OCV profiling is done. And then again, they are used as a second life battery, especially for the slow charging, probably charging with solar or something like that. And this will, again, it will talk about so these are all some of the parameters where the second life usage, again, needs to be defined. The obtained temperature, you have to be really careful when you make when you sort the cells, you have the data, so you'll have to look into these things before. It's not that, okay, you got cells, you did all this and you send it back. You'll have to look into this operating temperature, what is happening, how much is heating with the operation, and the depth of discharge, what seems ideal. The whole idea is you are supposed to look at all this and looking into the fact that the batteries simply don't heat up, because if they're simply heating up, you're looking at batteries experiencing thermal runaway or short circuit, or it could be many things. C rate of charge discharge has to be low, so solar makes sense. 5 to 6 hours, 9:30 to 2:30 p.m. some areas, 9 p.m. to 3 p.m. also. 5 to 6 hours charging is amazing. You could do that. Discharge also, it should be 4, 5, 6 hours of discharge, not like EVs. So rated SOH, again, you need to see the EOL. Again, after that also, you need to define, you need to test, study the cells. Again, this change from manufacturer to manufacturer, because every manufacturer has their own secret sauce, which defines how long their battery lasts, and the composition, the binder that they use, and the composition of the binder, how it is used. Yeah, so all these things, because they define how long the battery is going to last. So like I just explained, the batteries are disassembled, and they go for second life, and once they retire from second life, then that's about it. You're supposed to recycle them. So second life is generally energy storage system. And then safety warning. So just wanted to give a safety warning before we end this session. Usage of lithium-ion cells without a protective circuit should not be attempted, because the cells do not know when to stop charging or discharging. Charging and discharging lithium-ion cells beyond its specific limit of operating voltage can damage the cells. In some cases, can catch fire. Lithium-ion cells must not be charged and discharged at currents beyond specified limits. Lithium-ion cells must not be operated in temperatures beyond specified limits. So that will be all. Any questions? I'm taking questions right now.
Rahul, there are a lot of questions in the Q&A box. Many of them I'm sure you will be able to help with. For the verbal Q&A, let's mark some time towards the end.
Okay,
Any
sure.
questions in the Q&A box you can answer by typing anytime.
I'll do that. I'll do that.
There are a lot of questions already. Yes.
Okay,
Okay.
I'll do that. So you can, I will type over there. Thank you.
Thank you so much, Rahul. You packed a lot of information in those 20 minutes. Thank you for that. So next, I will invite Mr. Preetesh Singh. And Preetesh, kindly share your screen. And we will hear about the global market for lithium-ion cells, the raw materials, supply chain, and current status of lithium-ion cell manufacturing in India. Over to you, Preetesh.
Is my screen visible, Priyaksha?
Yes, now.
Just a second, please. Thank you very much, Priyakshi, for the opportunity to talk about our views around lithium-ion battery supply chain challenges and possibilities in India. A very warm good afternoon to all the panelists as well as the audience. This is, I think, going quite well, and Rahul has already covered a lot of technical information. That gives me a very good base to talk about the market information. So thank you very much, Rahul. Now, before I begin, I would like to talk about what all I'm going to cover during the presentation. So I'm going to talk about mainly 4 areas. One, briefly in the beginning, I'll touch upon the electric vehicle market, which includes trends in global as well as India. Then a little bit of cell chemistries and raw material, mainly from the point of view of availability as well as the applications in India. Then I'll deep dive about the battery supply chain globally as well as in India and the possibilities in India. And in the end, I will talk about our viewpoint in terms of India becoming a cell manufacturing supplier, that too for the Indian as well as the global OEMs. If I talk about the global market, so in the past, the growth has been phenomenal because of the probably the low base in terms of the CAGR. So the market has been growing by more than 53% of CAGR, dominated by China and then followed by European Union and United States. Then a little bit about the kind of applications or the kind of batteries are there actually different in different geographical areas. So I would like to talk a little bit about the kind of applications in different geographies that also reflects into the kind of battery chemistry what these markets are going to adopt. So in China, EV sales is distributed almost all by battery sizes. So from 0 to 20 kilowatt hour to 80 to 100 kilowatt hour, you will see the equal distribution, a little bit of not trend in 40 to 60, but otherwise it's equally distributed, mainly because of a small battery capacity, which indicates high penetration of small cars and availability of multiple electric vehicle options in China. Then on the right hand side of the chart talks about the trends in European Union, wherein you can see that this market is concentrated towards mid to high battery capacity. Moving on, the North American market, if you look at it, is completely dominated by very high battery capacity, around 80 to 100 kilowatt hour, mainly because of the kind of vehicle applications as well as the manufacturers, which are mostly Tesla and General Motors. Then in the end, we talk about the Asia Pacific market. So in ASEAN market, mostly it is dominated by mid-size EVs and still it's early stage of growth. So if you look at the applications in India, you'll find current applications somewhere here in the battery capacity of 20 to 40 kilowatt hour. And moving forward in next 5 years, also we are going to be somewhere here, not moving the mass market beyond 60 kilowatt hour. If you look at the electric vehicle growth in India, so in 2021 and 2022, the growth has been phenomenal. This is the 4 months data only. So if you look at the data for entire financial year 22, current calendar year 2022, the market is going to be like almost double than the previous years. So the EV momentum has started in India, and in different applications, including the passenger car applications, there are a lot of sales happening in India. So if we look at the globally, what kind of applications are going to gain momentum in terms of the energy storage? So in terms of energy storage, the entire demand mostly is going to be created by passenger electric vehicles. And also a second major contributor is going to be the commercial electric vehicle. So to summarize, even the entire annual demand by end use, if you look at, is going to be dominated by the passenger as well as the commercial vehicle, which means the dominance of electric vehicle is going to continue. So now I'll move on the cell chemistries and the raw material status, wherein I'll touch upon the global status as well as the applications in India. Rahul has already talked about different battery chemistries. So in different battery chemistries, and we have also received several questions around what kind of battery chemistry is suitable for what kind of geography. So this chart gives a little bit of idea. So currently, if you look at the applications in India are mostly LFP and NMC. LFP in Indian conditions seems to be more safer in compared to NMC. But the negative point is that the specific energy is much lesser than the other battery chemistries. So for any geography, including India, it's a choice between cost, energy efficiency, specific power, safety, performance, and the lifespan of the batteries. Depending upon the market maturity, every country is adopting a different battery chemistry. So let's have a look on the existing battery chemistries, which Rahul has covered in detail, the technical part. So I'll just talk about few battery chemistries. For example, NCA, which has a very high energy and power density, but very poor thermal management. So as Rahul mentioned that if a company can invest a lot of money in the thermal management, then probably this can be one of the very good battery chemistries. Then we have the chemistries which are gaining momentum in India are LFP and NMC. LFP is a very low cost battery, but it has also a low energy density. However, in terms of NMC, it has high energy density, but the negative point is that it has very high reliance on cobalt and lithium, which makes this unviable, for example, for emerging economies. There are battery chemistries which are evolving, and next decade, probably we are going to see a lot of new battery chemistries, including lithium, sulfur, semi-solid state, solid state, lithium air, and there are several other battery chemistries also. But particularly for electric vehicle applications, we are going to mostly see the lithium sulfur, semi-solid state, and solid state batteries. All other battery chemistries might find application in EVs also, but mostly they are going to be in other applications like energy storage, etc. Just to summarize the current status of the technology in 2022. So if we compare this in terms of energy density and life cycle, so this is how the mapping of all kind of technologies which are currently available. So if you look at the very high energy density energy density, chemistries are NCA and NMC. But if you look at the positioning of LFP and NMC 111532, they have better life cycle, as well as they have a reasonably good energy density around 200 watt-hour per kilogram. If you look at the future, the change points are mostly going to be two. One, the introduction of new battery chemistries. And second, the advancement of the existing battery chemistries. For example, around 2030 or 2035, you will see NMC chemistries much more advanced, and also introduction of other battery chemistries such as solid state, aluminum air, lithium sulfur, zinc air, and also lithium carbon LTOs. So the ones which are in blue color are the new introductions in next decade. Moving on, China basically leads the entire lithium-ion battery manufacturing industry currently, more than 136 gigawatt hour of the capacity, followed by European Union and United States. Currently, if we look at the status of India, we have only we don't have much cell manufacturing happening in India. It's only pack manufacturing, and there are, I think, companies in double digits who are doing the pack assembly and capturing around 15 to 20% of the value which we can capture by doing the assembly. But as of now, cell manufacturing capability is non-existent almost. But in future, the market definitely is going to be led by China, followed by European Union and United States. But India very aggressively positions to capture the cell manufacturing. And as part of the PLI, we already have 50 gigawatt hour announced, out of which 30 gigawatt hour is already given to companies like Ola, Reliance, and Rajesh Exports, and probably additional 20 gigawatt hour is going to be awarded very soon. So India is very aggressively positioning itself to become a major cell manufacturing cell manufacturing country also. But obviously there are a lot of challenges to realize that dream. If you look at the economic importance and the supply risk of different critical and non-critical materials, if I just give the example of nickel, cobalt, and lithium, they are very high economic importance materials, as well as the supply risk is very high because of the unavailability of these materials in India. So if you look at the historical price trend of cobalt, nickel, aluminum, and lithium, so if the prices are going down, then probably the burden which we are having on the fiscal deficit is not that high because it's all import dependent. But so in that situation, probably India can manage. But the moment, if you look at the situation somewhere around the beginning of 2022, wherein the prices of cobalt, lithium, nickel, and all other critical materials have spiked like anything, so it poses a very huge challenge for India. So India has to consider some alternate options. Now let's have a look on the metal production and the metal processing capability. So in copper, nickel, cobalt, and lithium, and the rare earth materials, it's completely dominating by China. So wherever they have not been able to capture the metal production part of it, they have already went ahead with the partnerships and JVs and other kind of collaborations and gained the significant advantage in the metal processing distribution. So on the supply chain, China has a lot of control, and all other parts of the world have to live with it or find an alternate solution. So by looking all these things, if you look at how India should position itself, or the speculative projections which we can have for India is NMC chemistry phasing out probably the current one by 2035, and advanced NMC chemistries gaining momentum by 2035 or 2040. Then LFP chemistry becoming the major battery chemistry in India with 36.13 in 2035 and 49.65 megawatt capacity in 2040. Other than these two major battery chemistries, India in long term by 2035 and 2040 is going to have other kind of battery chemistries, including semi-solid, solid, sodium-ion, metal, air, and flow batteries. Because India aspires to become the LFP and NMC cell manufacturing hub, let's have a look on the component value of both kind of chemistries. So in LFP chemistry, the cell cathode constitutes around 21% of the entire component value, followed by cell anode, and also we have a good amount of pack components. So when I say that India is already making the packs, so probably the 29% value addition out of the cell manufacturing is already there. But in terms of NMC chemistry, if you look at the number, cell cathode contribution of cell cathode goes very high, which is around 42%. Why is this situation? Because of the NMC battery cathodes are very high cost because of the inclusion of materials such as nickel, manganese, and cobalt. So whenever there is a hike in the price, which I was showing one of the previous slides, you will see a very significant hike in the prices of the NMC chemistry battery also, because of the prices going high for the cell cathode. In Indian situation, if you look at the distribution of cathode anode separator, electrolyte, and assembly, then for LFP chemistry, we can achieve theoretically 69 to 90% of the value add. And because assuming that all other materials are localized, and some part of the cathode from the LFP chemistry can also be localized in India. But in terms of NMC chemistry, probably it is a very big challenge to move beyond 43% because of the components of cathode, or the material which goes into the cathode is much more difficult than the LFP chemistry. Moving on, I'll just summarize the supply chain challenges which India is facing. So in terms of overview, the risks are posed by the supply chain policy and regulatory frameworks, technology transfer, financing, and the market availability. Then in terms of raw material, which is also a very big barrier in terms of securing the domestic manufacturing growth, because we mostly rely on imports, and because of the unavailability of such materials in India. Until or unless this supply chain challenge is not solved, even India will not be able to address the national objective of moving towards alternate fuel, which is managing the energy security, carbon emissions, and manufacturing import dependence. So if we continue taking raw materials from outside, then these national objectives are not being met, mostly the manufacturing import dependence as well as the energy security. So India has to somehow capture some part of the value chain in terms of raw material as well. Third bigger challenge is the financing, because the financial institutions are currently imposing a risk premium on their investments, making low cost financing a barrier. So this is a supply chain barrier, as well as if you look at the other part of the value chain, for example, the vehicle pricing, insurance, etc. There also the financing is a very big issue. There are several companies which are saying that they are solving such challenges, but I think there has to be major push from the policymakers as well as the private organizations to address such challenges. Then in terms of operations, we have lack of technical expertise and knowledge pertaining to the sector. It's a new sector. If you look at the historical pricing, India has focused on the market creation, then the charging infrastructure building part of it, but we really never focused on making the resources also available for such humongous growth which we are seeing now in electrification. So if you go back and look at the historical policies, which started with MNRE incentives in 2010, followed by National Electric Mobility Mission Plan in 2012, followed by FAME 1 in 2015 and FAME 2 in 2019. No policy basically covers the training and development of the skilled labor, because till let's say last year or last year, the debate was still going on which technology is better, whether electrification solves the national objectives or not. And India, despite several efforts and right policies, was not able to kind of get the kind of market creation which we were supposed to get. So the entire focus was there. But I think it is a right time now to go full throttle on making resources or the people available, the skilled workforce available for electric vehicle across the value chain. So we are talking about the batteries. So in terms of batteries, if you look at the entire product development process, you have some part of the R&D process, then the manufacturing, design, development, everything. So we can pick and choose. And state governments as well as the central governments can play a very significant role. For example, Tamil Nadu has an existing IT industry, and they also have engineering service organizations a lot in numbers and doing a very good quality job. So they can have a policy which promotes making training R&D people and making available across the country, even globally. And central government has to have at least taking a leading role in this as well. So there are, then the challenge number five is in terms of policy regulations and taxations. So the discontinuation of policies on tax holidays and reduction of accelerated depreciations also resulted in some kind of challenges for the supply chain. So that has to be addressed. Then challenge number 6 talks about the technology and material science. R&D is required for identifying technologies suitable for Indian market in long run. If you look at the traditional automotive industry, how it has grown in India, so you will see a very significant trend of technology collaborations. In India, Indian component manufacturers going abroad in Japan, Korea, US, Europe, and doing the technology partnerships with those organizations. But in electric vehicle industry, especially in the battery value chain, it is challenging to get a partner also, the renowned partner who is ready to kind of share the technology, because as of now, everybody has a lot of demand and they are full of demand and limited capacity. And making such collaborations is also a time-taking process specific to this industry. Then in terms of the market, which is the also one of the supply chain challenge, because unclear market demands will be an issue. There will be uncertainty or security related concern when it comes to resale value or in terms of the overall numbers also. So in terms of overall numbers, any supplier, any supply chain partner will be ready to establish in India if India has a very unique and certain target, that 30% or 40% conversion by certain number of years, or proximity to any supplier base. I think on both the parameters we have challenges, so that has also to be addressed in some way. Moving on, possibilities in India. So India, in terms of policy making and also in terms of implementation, India has been very consistent. So since the beginning, the focus has been on the localization. And until or unless you localize the battery, you are not really localizing, you're not really gaining much advantage, because 20%, let's say 40% is material and then 20% is pack cost and another 20% is cell manufacturing. So around 60% value India can generate if we are able to localize the entire battery manufacturing in India. There is an initiative called as PLI scheme, in which 3 companies has been awarded: Rajesh Exports, Ola Electric, Reliance, and 30 gigawatt hour capacity has been allocated, and probably the next 20 gigawatt hour capacity is going to be allocated very soon to the other value chain players. And India seems to be confident about achieving this, and the major focus has always been on the localization. So in terms of battery also, if you look at the battery components, they are also being pushed through the phased manufacturing program. So initially the custom duties on the components are very low, but going forward, which is kind of linked also with the 60% value add which India is targeting, the custom duties are being increased. So that you have a 50 gigawatt hour battery, lithium-ion battery cell manufacturing capacity within 5 years, and that is also a localized one. That is going to give a lot of advantage to India, but that is not possible only by collaborating with local players. So across the value chain, from raw material to cell component to battery data to sustainability, there are good global players, and effort has to be made to find out some way to collaborate so that we can benefit the connected global supply chain, because dependency on such technology is very high on the global supply chain. There are companies which are part of the PLI scheme have well-placed plan to achieve whatever they have been awarded, as well as the 60% value add. So these are some of the information for the 2 companies which are part of the LIV value chain. So thank you very much. I will take questions when we open up in the end for the questions. Over to you, Priyakshi.
Thank you so much, Preetesh. A wonderful presentation, and we've already seen a lot of good comments on the insights that you have presented over chat. So thank you so much for gathering all the information and presenting it so nicely, so comprehensively for the audience. Thank you so much.
Thank you very much.
So after covering the first part of the event, that was more about the market overview and the basics of lithium-ion cells. Next, we will move on to understanding the manufacturing nuances and the quality control. So to begin that part of the event, I would again invite Mr. Rahul Bollini, who will start with his presentation on the nuances of lithium-ion cell manufacturing. And after that, we will move on to two presentations related to quality control of cell manufacturing. So Rahul, if you could share your screen. Rahul, are you there? Oh, yes. Yes.
Thank you, Priyakshi. Let me begin.
Right.
So let's talk about lithium-ion cell manufacturing. Components of a lithium-ion cell. There are four major components: cathode, anode, electrolyte separator. We'll be talking in depth about this. This is a photo from Samsung SDI representing the cathode, anode, electrolyte, and separator. Types of lithium-ion cells, basically, it's generally categorized into three grades: EV grade, ESS grade, and potable. Potable is pretty much that you see in handheld devices and all. And we'll be talking more about EV grade, ESS grade, because the numbers are huge, and it's a market where the battery packers and all are taking more interest. Portable is pretty much one or two cells that you're just integrating, not much of a smart BMS or something like that, a basic PCM for the safety. So EV grade is designed for electric vehicles, and ESS stands for energy storage systems, and these cells are designed for energy storage applications where they might not have the ability to charge very fast or give that kind of high output, but they are basically long cycling characteristics kind of cells. So let's talk about EV grade cells. They have low internal resistance. IR values will be less. They allow for fast charging, because fast charging is, again, inversely proportional to the IR value. Lower the IR, higher the fast charging. They have maximum continuous discharge capability. So you might have heard in the market people talk about 3C cell, a 5 Ah cell giving 15 amps of maximum continuous discharge, or a 2.6 Ah cell giving 7.8 amps of maximum continuous discharge. So this is what the EV grade cells are. And EV grade cells have lower cycle life when it is used in EV application. Let's talk about ESS grade. Their IR value is high, hence it cannot be fast charged. Their C rating of discharge will be on the lower side, possibly 1C, 1.5 sometimes. And but they're designed in a way that they charge slow, they discharge slow, but they last long. Actually, it's longer actually. So 3 stages of cell production. So we'll be talking about that. And the first process is the electrode coating, and then the cell assembly, and then the third stage is the cell formation, aging, and grading. Yeah. So first is the electrode coating. Let's talk about electrode coating. So basically, the raw materials come. Obviously, not all raw materials can be manufactured by the cell manufacturers. So when the materials come, there's IQC for process in place to see the quality of the materials. There's an random sampling to see if the materials are having the characteristics as per our requirement. And after that, basically that's called as raw material characterization. And then the cathode anode slurries are made into slurries in their respective mixers. In mass manufacturing, generally dedicated mixer will be there. If it's a laboratory, people could reuse, although it requires a lot of cleaning efforts and all. And cathode and anode slurries are coated on their respective slurries after the mixing is done. It's coated, on the respective current collectors. So generally it is aluminum for cathode and copper for anode. Copper is required there for the electrons to move in and out. And the coated current collectors undergo drying process. There'll be multiple ovens where you will have to, where different temperatures are set. And once it comes out of there, then it goes to calendering. So calendering, the whole idea is it has to be even. So dried electrodes undergo calendering to ensure the coating thickness is even, and after that they undergo slitting. So slitting will be for cylindrical and prismatic because they follow the winding method, and it will be called punching for pouch cells, where it is made into small pieces. And next process is the cell assembly. Before the cells are taken further ado, they will have to undergo vacuum oven. They are put there so that any solvent, generally NMP solvent is used for cathode, water, deionized water is used for anode, so that any of the moisture from it is 100% removed, or like close to 100% of it has to be removed, or else the cell activation, when the electrolyte is put, the issues will come. And then the electrodes are welded with the respective tabs, generally aluminum tab for cathode, copper coated with nickel tab for anode. This is what the standard is. Although you're free, you can feel free to change it, but this is what the industry has adopted. And then the electrodes are winded in terms of cylindrical and prismatic, with separators next to each other. And in pouch cell, it will be a Z stacking. Very soon we will see the representation image of that. And then the winded jelly roll or the Z stacked roll from the pouch cell, they are put in their respective housing. So in pouch cell, it will be aluminum plastic film. In case of cylindrical cells, it's going to be 18650, 21700, or whatever the dimension. The SS is basically made up of stainless steel, and the prismatic cans are pretty much aluminum. And then the electrolyte is filled, and then they are sealed and kept for resting for the wetting or soaking process of the electrolyte. And the third process, this is where we actually know what grade the cell is made. Earlier, it's very difficult to see because the way it has been coated, whatever accuracy, whatever we do, 100% accuracy cannot be expected, because say while cutting, the accuracy can be off by 1% or 1.5%. Again, electrolyte filling, it can be off by say 1%. So a little bit of variation comes, and that is where in the final grading you get to know. But cell formation is the first time charging of the cell, and this process includes charging the cell at various C rates until a certain SOC is reached, and then the voltage of this, the OCV of the cell is checked. In case of pouch cells, there's an additional step of degassing, because the aluminum plastic film of the pouch cell is not as strong as cylindrical and prismatic, and hence they will bulge. That's why there is an additional channel created for it, so that the gases can be stored in another place, and then that can be cut off later after the degassing process. So that process is called degassing, which is done after the formation. The C rate and SOC to be reached in the process of formation and all that varies from cell manufacturer to manufacturer, and again depends on the raw materials, the cathode that is used, the anode that is used, the composition of it. So it's one of the secret sauce kind of thing. And then the OCV of the cells are monitored under high temperature aging and then with normal temperature aging. They see how the OCV of the cell is dropping, basically self discharge of the cell. That is how the grading is actually done. And grading is basically done based on the following parameters: the capacity of the cell, how much it's holding, and the ACIR, DCIR values. Like I said earlier, DCIR is done by the cell manufacturers. You don't need to worry about that. That's why ACIR is pretty much done by all battery packers. Then OCV of the cell at a particular SOC, the self-discharge rate, cosmetic aspects. Suppose if there is some kind of scratches or some kind of dents or the bulging or something like that, that will be not passing under A grade, A minus also. It will come under B grade generally. So cells are graded as many grades within A grade, A minus and B grade. It can go on. You can go to C grade also. And for example, within A grade also, you can see A1, A2, A3, A4, and so on in A grade. And it necessarily does not mean that A1 means best. Generally, the assumption is always that A1 will be the top. It's actually the other way around. A1 is the least kind of A grade, to be frank. But again, it depends on manufacturer. Everybody has their way of coding. So whenever you discuss with cell manufacturers, you can ask them about this. They will tell you if they feel that you have the potential to work with them, or you promise them good volumes, or they see good business potential with you. So they will reveal all this. So I have worked with a lot of cell companies, so I have a fair understanding. Cell manufacturers, so they are open to me. And yeah, so again, so probably A4 will be the highest capacity. Again, the highest capacity does not mean that the cell is the best. Again, there is a saturation where the cell stability is on the higher side. So there's a lot of things that go in. So that's why many companies, they struggle to get the right kind of cells. And when they are making packs and all, then there are a lot of issues and all those things. Again, more capacity, like I said, but generally A grade is better than A minus, which is better than B grade. So this is how the grading is done. So these are all something which is done at a cell level. Important factors during cell manufacturing, I thought we'll cover. So these are all. So if at all any of you is working in cell manufacturing tomorrow, whenever you make a cathode, the positive electrode, you will have to look into this kind of parameters, the electrochemical characteristics of cathode active material, which is also known as CAM. The physical characteristics. Electrochemical would mean how much is the discharge capacity or the specific capacity of it. Physical would mean the particle size, the D50 of the material, and you'll have to do SEM for that, scanning electron microscope, and mixing ratio of the cathode active material, the binder, which is generally the PVDF. It could be emulsion based or suspension based, again completely up to the cell manufacturer. Carbon black, which is added for conductivity. The solvent, which is pretty much NMP, and the market is slowly shifting to aqueous based, which is already a method adopted in anode. And some people use CNTs and many other things you could use, but it's all, like I said, these are all some of the things. And the mixing ratio, the materials matter, and the mixing ratio, that's what defines a good company from a better company. So, and the type of material that is used for the positive current collector, which is pretty much aluminum as of today, and the thickness of that. And if it's LFP, some people go with carbon coated aluminium for LFP, especially in Asia. It's a very big thing. In your Western countries, they have not really started, so they are pretty much using the normal aluminum thing for the NMC. And then again, the coating thickness during coating and after calendering, coating thickness of the cathode material on each side, or after the, or both sides together taken. Anode, it's a similar process where the negative current collector is going to be copper instead of aluminum. And generally this is ED copper, which is electrode deposited copper. That's why it's slightly on the expensive side. And generally also anode is expensive because generally also copper is expensive because today's LME price is almost thrice. Copper is thrice as expensive as aluminum. And again, the density of copper, which is close to 8.97 to be frank, which is on higher side compared to 2.7 of aluminum. So 3:10, and again the price is almost 3 times. So you can imagine the copper adds a lot of cost, and it is something which has been eliminated in sodium-ion batteries. That's why people say sodium-ion batteries cheaper. This is one of the reasons why sodium-ion batteries are cheaper. They use both aluminum cathode and anode. And coming back to this, pretty much similar to cathode. Then electrolyte base salt, which is popularly LiPF6, with this lithium hexafluorophosphate, and then the molar ratio 1.0 m of LiPF6. Some people want 1.2. Again, it's all up to them what they want to select. And again, the base, generally EC along with DEC, EMC, or DEC, DMC. So these are all some of the things. And the ratio of this, all this ethylene carbonate based things, the organic solvents, the ratio of that, and again the additives which make the cell stable during fast charging and all, and life also it gives more, which is VC, which is vinylene carbonate. And then there are many more that again it's all secretive. And the percentage of usage generally shouldn't be more than 1.52%. Generally can't add too much of it. And the separator, so thickness of the overall separator does matter. Starting from 16, I have seen 16 all the way to 25. Some people use even lesser. Number of layers, it could either be single PP or PP plus PP, or PP plus PE plus PP, which is polypropylene and polyethylene. And material of each layer, like I just said, thickness of each layer of the separator, porosity. Porosity does play a vital role that will decide how. It cannot be too high, it cannot be too low. There must be a balance. Generally 40-ish is what is preferred. And puncture strength in grams, at a percentage of tensile strength, a TD and in TD and MD direction in kg per centimeter square, and again the shrinkage of the material at 90 degrees per hour. And again, there are other temperatures also that can be done. Yeah. And other components, type of material for positive tab, which is aluminum tab, and this will be copper coated with nickel for the negative, and then the thickness of the positive tab, the width of it, the number of tabs. Suppose a cylindrical cell, 6 Ah cells comes with 3 tabs. So because single tab is not enough, a big cell having 6 Ah, having a small, very small tab is not really good, and the tab is not really wide also. It can be as low as 4 mm. So that is a concern always. So that's why these days some people have started multiple tabbing. In fact, there are some power grade cells which have even high number of tabs, but that will bring down this the energy stored in the cell, and the capacity of the storage of the energy will come down. Again, the cell weight will also increase. And but yeah, so there are many ways how you can play with the design of it, and that's the end product. So there is always differentiation. No two cell manufacturer will have the exact same kind of composition or the raw material and all. Everybody has their preferred composition and the supplier and all that. So coming back to this again, the housing, like I said, cylindrical, pouch, prismatic, the based on the housing they are classified under those names. Fabrication process, I thought I'll just play a small video. Just this is a small video from a pilot plant in Malaysia. They were more than happy to give it out. So these are all basically the cathode, the carbon black, and now the solvent is being added. Viscosity is being checked, and then it will be coated. This is the coating, and it's coming out. This is called roll to roll coating, coming out of oven and then being calendared. This is a slitting process where you can cut the electrode into multiple cuts. This is the tab welding. This is for a cylindrical cell, so the tab is being welded. That is the top with the cap. In cylindrical, you'll have to use two separators, so that once the roll is done at no given point, the electrodes are touching. And the tallest of these rolls will be, the widest would be the separator, to ensure that it does not touch. Because if it touches, that cell shorts, that is short circuit, internal short circuit. So once the electrode is the jelly roll is made, there's a short circuit test which is seen, which ensures that okay, there's the cathode and anode is not touching at any given place. So, and then it is put in the oven. Again, you can do that before you put it in the can for the electrolyte filling, because electrolyte should never ever feel any kind of moisture. It's highly sensitive to water. like I said, Electrolyte is very, very sensitive. So it is done in a very high, very low ppm dry room with very sensitive conditions. So that was the cell activation part. And then I'll share the YouTube video link of it, so you people can also watch it. I think audio didn't. Yeah, coming back to ours. So this is a small representation image that I could take. This is a very sensitive field. Not everybody is willing to share. So that's how I try to compile with whatever possible things. So this is for the cylindrical. You can see this is how it is internally. And then pouch, it will be multiple tabs which will be added. And then a final tab will be there. And pouch cell is slightly expensive because of the tab. Tab used here is really, really expensive, the thickness of it. And hence, pouch cells have low internal resistance. And for high power or high C rating and all, pouch gives you wonderful this thing connection, current output. Prismatic, this is the prismatic thing. And to be frank, it's all pretty much the same in cylindrical and prismatic. Only thing is, cylindrical is going to be round and prismatic is going to be wide. So you just put it inside and all. Prismatic is the most expensive because the amount of things that go inside. Electrolyte filling is huge. You are supposed to overfill the electrolyte in prismatic. So that issues that adds up the cost, and the aluminum case does not come cheap as opposed to stainless steel case in cylindrical. So SCI layer, I thought I will add this additional thing. SCI is a solid electrolyte interface which is formed during the first charge process, and it is usually a few nanometers thick. So when you first charge, there will be a small layer that is formed. I'll just show over here. Yeah. So this is the SCI layer. So this ensures that the electrons, whenever you charge the battery, electrons stay on this side and they don't come out this side, because if electrons flow the other side, and then the battery will not be able to give the kind of output. So SCI layer is very important, and the formation process ensures that SCI layer is formed in a nice way. It shouldn't be too thick, it shouldn't be too thin. And SCI is the first thing whenever a battery is catching fire, when the battery is going high temperatures, the first thing that disintegrates is the SCI. And even if you cool down, okay, if the battery does not catch fire, but once SCI layer is damaged, you're looking at cell bulging, and it will not give you that kind of capacity. So that's a very bad thing that happens. And coming back to this importance of SCI layer, if that layer is intact, the longer it is, it'll give you long life, good cycling. So good cycling would mean the round trip efficiency of this thing, and high performance, high safety, and high stability. And like I said, this is the SCI layer. So any questions? I can take questions. Yeah.
Thank you, Rahul. Thank you so much. Very informative presentation. Thank you for putting it together. So after the manufacturing, let's move on to the last two presentations of this webinar. So we will first like to invite Mr. Franco from Marposs to start his presentation on testing operations in lithium-ion cell manufacturing.
Hello, good afternoon, everybody. Okay, thank you, Preetesh. Let me try to share the screen. Just a second. Okay, can you see in presentation mode, or should I swap?
Not yet, it's still small.
Okay, let me swap. Is it better?
Yes, yes.
Okay, very good. So, thank you again, everybody. So let me introduce myself. My name is Franco Stanghellini. I work for Marposs Group in the headquarter office in Italy. I'd like to spend just a couple of words on Marposs Group for who are not familiar with our organization. We are an international company specialized in the manufacturing and production of solutions dedicated to gauging, inspection, and testing in the for quality control and process control and monitoring in the manufacturing process. We are a major supplier for the automotive industry since many years, and we are active in the field of batteries as an interest in the transition from internal combustion engine to electromobility. Just a few numbers about our group. Today we are about 3,500 employees worldwide, with, as I said, headquarter is in Italy, where I work. But we are present in about 34 countries with our own sales and service organization. For what concerns India, our headquarter is in Manizar, near to Delhi. But we have more offices, and we are about more than 100 employees in India. Let's focus more now on what is the main topic for our presentation of today. As I said, we are active in the automotive market since many years, 70 years. We have the 70th anniversary this year. And we are consequently absolutely involved in playing a key role also in the transition from internal combustion engine to electromobility. For what concern this specific topic, we have reorganized our group with different competence center, and mainly we have today, for what concerns the topic related to battery market, 3 main companies of the group which are active in this field. Our headquarter mainly for gauging and inspection products and application, and 2 more companies in the north of Italy mainly focused on leak testing and electrical testing and end-of-line testing, which will be the focus for today's presentation. But as I said, we have seen before an overview along the manufacturing process of battery cells, starting from the first operation up to the complete production of the cell. We are, as a matter of fact, involved in any kind of quality control and process control and monitoring operation along the complete manufacturing chain. Here, just to make an example, for the operation that we have seen before for the manufacturing of the electrodes, so starting from the rolling of the metallic sheet to the coating and drying, calendering and slitting operation, we have a wide range of products that can be used for the quality control on the line, based on a chromatic confocal, interferometer, laser micrometer, or other kind of sensor. I do not want to spend more time on this because I'm moving straight to the main topic of our presentation today. For today, we are focusing more on topics related to testing operation on the manufacturing process of the battery cell, and more specifically to the topics related to leak testing and electrical testing. Let's start with a few words about leak testing. Leak testing, I would say that is a crucial operation for almost all the components of a battery system. Okay, the verification of the perfect sealing is something that must be performed along the complete manufacturing chain, starting from the production of the cell, in some cases also for the assembly of the cell into the module. For sure, other components that must be perfectly sealed are the components of the cooling circuit and components of the battery pack and the complete pack assembly. It's clear that the reason for the sealing requirements are different. Also, the specifications are clearly different. Talking about the battery pack, for instance, it's clear that what you expect to have is a perfect sealing that will prevent the entrance of water into the battery pack. So, in other words, what you expect to have is the compliance of your product to IP specification, IP67 or 69, whatever it is. For the cooling circuit, we will expect not to have any leakage of the cooling fluids. But for today, the main focus will be on the battery cells. For battery cells, you are also expecting to have a perfect sealing. And the reason of this is that you are expected to have definitely no leakage of electrolyte. This is the first important point, because the leakage of electrolyte would progressively reduce the performance of the cell, but also because the electrolytes have typically solvents that could react with the ambient moisture and generate also dangerous materials, dangerous compounds. And of course, you also do not want to have moisture to enter the cell, because also this would probably generate a failure of the cell. So, what about the leak testing methods? The most frequently used testing method in the manufacturing of industrial components are based on different technology. Typically, air testing method like pressure decay or mass flow can be used in a range of leakage rate, which goes from 10⁻⁻1 up to 10⁻⁻3 millibar liter per second. While when you expect to have a higher sensitivity, helium as tracer gas in vacuum chamber is the method that is most frequently used. And this is the technology which is most frequently used when talking of leak testing of battery cells. The testing method based on helium in vacuum chamber is in essence a method where it is requested to have the tested part, which is put into a testing chamber where you make the vacuum simultaneously together with the vacuum into the part. Afterwards, the tracer gas, most frequently helium, is blown inside the tested parts. And finally, in presence of a leakage, this helium will leak out of the part and will be detected, will be driven to a leak detector, usually a mass spectrometer, that will evaluate the amount of leakage that you have on your part. The use of helium is because this is inert gas, light, not ignitable, and not toxic. This is a method that I said is guarantees the highest sensitivity. It is fast. It's a global test. It is generally accepted by any norm. So let's have a look along the manufacturing process of battery cell when it is possible to perform leak testing, or when it is usually requested to perform the checking of the perfect sealing. A part of the possibility of testing the housing alone, which is something that is also done. The first operation where typically is requested to perform leak testing is after the introduction of the electrodes and separator, the stack of electrode and separator into the housing, and before adding the electrolyte and making the final sealing of the cell. Doing the test at this stage is one possibility, or at least it is something that will guarantee the possibility to check the sealing in some position, but other leak testing operation could be required after the electrolyte filling and the complete sealing of the cell, or after deformation, and possibly after degassing and resealing. We have seen in the presentation before that in many cases, depending on the type of cell, it could be requested after the activation of the cell, after formation, to perform a degassing and the new sealing. And finally, also at the end of line testing stage, it could be requested to perform the testing operation. So what we've seen before, testing with helium in vacuum chamber, it is typically done before electrolyte filling and sealing. Here is just an example of a machine which is designed to make the test on 8 prismatic cells simultaneously. But what about testing when the cell is already finished, totally sealed? So that means already electrolyte filled in and the cell already sealed. There are methods that can be applied also based on the use of helium in vacuum chamber. One could be applied only for some type of cell, for instance on prismatic, adding helium together with the electrolyte before sealing, or the bombing. Both are based on helium, not on all type of cell. It is possible to apply this kind of method, especially bombing. It is a method that is not definitely suitable for an industrial process. So what we typically propose in a case like this, especially for mass production, is to use a direct tracing of the vapors of the solvent of the electrolyte, something that you already have in the cell and that you do not need to add to the cell to verify the perfect sealing. There are solutions available on the market to perform this test in a laboratory environment. What we have developed is the possibility to implement this kind of technology into testing for mass production. Is a method that, of course, is based on the type of electrolyte that we are going to trace. It could be the methyl carbonate or a different kind of solvent which is used. So a proper selection of the best solvent to be traced must be done. Afterward, to identify what are the testing parameters, the optimization of the cycle, having in mind that we are talking in this case of development of machines dedicated to test in mass production. So something that must be reliable, repetitive, and first of all, fast. Here is just an example to the comparison of a reading of the tracing by the dedicated specific quadruple mass spectrometer, which is used for the test, making a comparison between the background and the tracing of a leakage of dimethyl carbonate and a typical signal detected when making the test, for instance, using calibrated orifices of different size, checking the vapor of electrolyte. So where you can see that it is possible to detect leakages having the size down to 5 microns in your cell. And here is just an example of an automatic machine for mass production. In this case, we are talking of a machine for a type of battery that it's definitely not produced for the automotive market. In this case, we are talking of coin cells, but a similar approach can be proposed also for different type of cells. Let's now have a look at a different type of testing. Also in this case, we have seen in the previous presentation the importance of performing specific testing operation to qualify the main functional parameter of batteries. As a group, we are active at different levels, so that means we propose a machine for testing in the manufacturing of battery modules, battery pack, and of course also battery cells. The testing operation that can be performed could be at the end of the line, so the final qualification of your product, but also at the beginning of the line. For instance, when you want to assemble the cells into a battery module or a battery pack. This is a typical example. In this case, we are talking of a machine which is designed for low production rates. So it's not a machine for mass production, but is a machine that can perfectly match the typical testing requirement for pilot lines or for low rate production, and that can be used either for end-of-line testing in a manufacturing line of battery cells, or as a beginning of line in the assembly of a module. In this case, we have a machine, for instance, where which is based on a rotating table concept. On one side, you have the loading and unloading area. Is a machine predisposed also for manual loading, so protected by light guards. On the right side, we have the testing area where we have implemented different type of testing operation. The QR code reading, dimensional gauging, electrical testing, insulation test, and finally, as an option, also the leak testing. Just have a better look at these different operations that can be all of them necessary to correctly qualify your product. First, QR code reading is definitely a must to guarantee the compliance with the Industry 4.0. So all the data which are collected and elaborated as this machine can be stored in association to the QR code of the part, so in order to have a perfect tracing. In the second operation, we are talking of dimensional measurement and more specifically of thickness measurement. In this case, this is a machine designed for a prismatic cell. So one of the issues for the prismatic cell, but not only for the prismatic cell, could be related to the possible swelling of the housing of the cell due to the incorrect formation process or not perfect degassing after the formation process, or even production of additional gases after the degassing operation. So the measurement of the thickness could be also a method to detect the presence of possible swelling or other kind of dimensional errors in the cell. In this case, the technology could be based on contact measuring method, or non-contact thanks to the use of chromatic confocal technology. Next operation, which is always required, is related to the functional testing. You have seen before which are the different methods, different parameters that is typically requested to perform. We have seen the most frequently parameters which are used to qualify a cell are the open circuit voltage and the internal resistance, elaborated as ACIR parameter at different frequencies, usually at 1 Hz and 1 kHz. Of course, in a machine like this, it is possible to perform also different kind of tests, DCIR or even complete capacity measurement, it's clear that depending on the type of test, the cycle time will be different. Will be different because some testing procedure like DCIR or capacity are definitely much longer to be performed. Next testing operation, which must be also always be performed, is the checking of the perfect electrical insulation. Usually, this is always done, for instance, on prismatic, but not only on prismatic. An insulating tape, it is wrapped on the cell, and it is necessary to verify that there is a perfect insulation of the two electrical contacts respect to the external surface of the cell. So in this case, we have an electric foam, which is disposed on the different actuators, horizontal and vertical slides, in order to contact the complete surface of the cell and verify the insulation resistance and the possible current leakage. And then finally, we have seen before, the possibility to integrate, in this case, the leak testing. Of course, we are in a stage of the process where the cell is completely sealed, so there is no way to add the tracer gas inside. So in an operation like this, electrolyte tracing would be a must as an option for leak testing of the cell. When the testing of the cell is completed, there is, of course, the possibility to classify the cell. We have seen before that a classification of the cell depending on the type of cell, depending on the size of the chemistry, and also of the use of the cell could be a must. In this case, a machine like this can be connected directly to the stores where the different classes are highlighted for the operator through lamps that in this way we'll have the possibility to classify the cell, putting them in the proper class. Of course, if we are talking of a manual operation, otherwise, for an automatic process, the same operation can be performed by a robot with the same, more or less the same concept. These are just two examples of the application field that we propose for the testing in the manufacturing process of battery system. It's clear that for any question or for discussion on possible needs and supply of customized application, we are at your disposal. Here is my contact, and of course also contact of our colleagues, which are in our headquarters in Delhi, Mr. Anish Arora. Thank you.
Thank you so much, Franco. It was a very insightful presentation, and you covered the breadth of lithium-ion cell testing. Thank you so much. Before we move on, I'll quickly launch a poll on the presentation that we have just seen today, and I would request all of the participants to mark their answers to it, please. So the first question is, does Marposs solution of leakage testing satisfy IP67 compliance? And the second question is, can electrolyte tracing method detect leakage of 10 microns? I can see many of you have already answered, but the ones who have not, we will wait for another couple of minutes. And then we'll move on to the final presentation for the day, which is by Carl Zeiss, Mr. Manoj K Sundaram, on the X-ray solutions for quality control of lithium-ion cell manufacturing. So another very interesting presentation coming your way. Just we still have a couple of around 20 people who've not answered. Please mark your responses and we'll move on to Manoj's presentation. Thank you. Manoj, please feel free to share your screen when you're ready.
Okay. Is my screen visible?
Yes, Manoj.
Okay, good. Right. So let me share it to the presentation mode. Is
Yeah.
it in the presentation mode now?
Yes.
Okay, thank you. Thank you, Priyakshi, EV reporter, and all the presenters who have really laid out the path for me to conclude or talk about quality. So as you can see here, cell construction, quality, and supply chain. I've highlighted quality because that's what I'll be talking about. And majorly it will be on X-ray solutions. My name is Manoj and I head the business development and I focus on electric vehicles. You can reach out to me on the email ID or the LinkedIn profile, what is mentioned below. As was shown in the previous presentations, we all are moving from the IC engines to different industries. One of them is the electric vehicle industry, which is shown there. So we have grouped some solutions around it. If you see an electric car, as you see in the screen now, there is a lot of power electronics, battery, which forms a key component because of which this show is happening. You can see the large battery tray, which is identified over here. Then it could be a fuel cell system too, and e-motor, transmission, and so on. Then while we are centering our presentation around cell, that is the cell manufacturing and the topics around cell, which have been laid out by Preetesh and Rahul, I would like to highlight that Zeiss as a company is providing you quality solutions around cell, and also around, we can go a level below, we can go down to the electrode level and give you solutions. We can go further down to the material and also down to the SEA layer, what Mr. Rahul was mentioning. Further upward integration, we can work on the modules and packs and also on the tray. So this is our widespread space where we talk about quality solutions. And to be a little focused, we don't measure electrochemical or chemistry or so on. Our major measurement when we talk about it is dimensional measurement. So any dimensions in all these areas can be effectively measured. As you've seen the process is simple. Okay, you have a R&D, you try to figure out what kind of chemistry you want, then you start buying the raw material, then you make electrodes as was shown by Rahul, and then the cell assembly and module pack assembly and show. Now, on the left side, you will find light microscopy solutions. They are into Zeiss light microscopes and Zeiss electron microscopes, which form a destructive method of measurement to look in depth into the anode, cathode, and separator. Today, we are going to talk about the CT or computer tomography or X-ray measurement solutions, which will be the focus for today, how we can use them for cell assembly. If you look at the measurements what are required in a single cell which comes out of your line, it starts with, if you see here, it starts with measurements from nanometers to centimeters. Starting with nanometers, you would like to understand what is the kind of particles what you buy. Are they good? Are they good after 1,000 hours of working, 100 hours of charge and discharge? If you recollect the topics of memory effects and end of life, how much charge is retained in a battery by Rahul. So all these topics, SEA formation, this comes in a few nanometer levels. Porosity and transport, possibilities in the cathode and anode, that comes in the micron area, then particle sizes and so on. We will focus on packaging, assembly, and layer quality and bulk defects. So these are the two areas what we'll focus on. At a later date, we would try to do a presentation covering the other areas. Repeating, we are talking about not external measurements. We are talking about in-depth understanding of what is inside a battery after it is manufactured. Okay, you have seen this slide in various presentations in the past. R&D and then cell assembly. And for us, all types of form factors and chemistry are same. We don't differentiate. We can measure all of them quite well, starting with 18650 to 2170, or even the blade batteries or the large ones, large format prismatic cells, all can be measured with ease. Traditionally, when you have to check a battery, what you had to do, you had to, as you see here, commercial 18650 battery, you had to cut down, you have to break it down, cut it open under an argon or an inert atmosphere so that it doesn't catch fire, then process it, make it good enough for viewing it under a microscope, and then you can view all the current collectors, active materials, and so on, and see what has gone wrong. So it is up to your assumption where you cut, what you do. You might also pull out a small strip, and then you will view it under different microscopes to understand what might have gone wrong. There is a kind of a experience, there is a kind of a skill set what is required to do this. You can look at under different lights, a polarized light or a bright field, to look at the individual elements. You can see a light amount of waviness. If you see this, you can see a slight amount of waviness. So these are all, and you can see a lot of cracks around in these areas. So see, these are the kind of things what a battery engineer would look at. Today, what Zeiss is trying to show you is we have 2D and 3D CT systems. When we say CT, it is computer tomography, similar to the MRI scans and the CAT scans, what you do in a hospital, but this one is for industry. So you can have a 2D inspection of the cell, you can have a 3-dimensional inspection of the cell, you can have a 4-dimensional inspection of the cell. So this is what we would see. What we would see in the next 10-15 minutes is only snippets. Any other details you want, please talk to us directly, or you can see it in the next screens. I have a few videos so that the topic can be understood easily. Just a minute. Okay, so this is a CT machine which is called a Metrotome, and this is how large it is. Now let's assume the part is in the middle. You can see it's a reflector. It could be a battery. I'll show you with a battery also. So you put the part inside. You mark the X-ray, and then you scan it. Then you can get a complete detail of what is what is inside. You can easily look at what goes on inside, and you can understand the different layers, which is very useful for a designer to figure out. Let us see if the video is completing. Let me go a little forward. So this can be applied for reflectors, cylinder blocks, or composite material, and so on, and also it will include the battery. So once you collect the data, it becomes like a CAD data of the complete battery inside. You can slice them, go through and look at what is going on. With a lot of understanding, you can do a CAD comparison too. How is this technology useful for the battery industry? For the battery industry, if you go a little deep, you can look at the battery material, you can look at the battery cell without housing, with housing, you can look at the electrode stacking, and so on. So these are all the descriptions of effects what we can do. In the cell assembly, you can use it offline or online, both are possible. Now I'll show you a video using the cylindrical battery itself. So the battery is picked up, you have a set of batteries, you pick up one particular cell or a set of cells, you put them in a small thermocol, you take the fixture, put it inside the CT machine, then you do a scan of it. This is an X-ray scan, the same machine, what you saw. Once it is done, this is a live scan image of what you can see inside a battery. This is a live image. The post-processing needs to be done. Once it is over, then you would have collected the complete 3D. I mean, I'm just exaggerating a little to say 3D CAD model, but you can see through all the complete layers of the cell. And this is possible. We are doing it, we are doing it for so many battery importers today in India. As Mr. Preetesh mentioned, we don't have battery manufacturing here, but we have this machine available in India. And a lot of people come in and, slice their batteries virtually, look at what is inside. They are able to get a lot of insights into what goes on, what has gone wrong. Is the vendor delivering what is required? You can see the clarity. This is a 3D view. I will subsequently show you a lot of 2-dimensional views, but this actually is a 3D view of the data. Going forward, this is another view of the battery inside. You can see the vertical battery on the right corner. We are slicing it down. You can see the gradation, -3, -4 millimeters. As we go down, you can see the central portion will become different. You will start seeing some changes in it. And this is a pristine battery, so you really don't find much of problems. But what is important is, as you go down to the lower portion, you can find out that different layers, different weldings, or the tab welding and all that, which you can see whether they are in correct shape or not. This is just another example of, just to make a little more clear. This is a Kinder Joy. What you can do with it, you can look at different materials and you can slice through and do a CAD comparison. So this is idea of CD. Just another view of it using a mobile phone. You can look through a mobile phone deep inside so that you can understand your complete process very easily without the need to destruct any of your batteries. You can look through them perfectly. For sake of time, I'm just moving forward. Okay, so we move from centimeters to nanometers, and this is the kind of SEI layer area, and few nanometers, so this cannot be viewed or monitored by anybody. This, you have to do a destructive testing. What we see, okay, let me go through. You might have seen this slide in many slides in Mr. Preetesh's presentation. This is the reason why you should check your battery thoroughly. Because basically you have to look at cost, safety, lifetime, aging effects, and there is always a trade-off between all of this. So you can measure all of these things if you have our solutions. Okay, now let's put deep. This is a prismatic battery. What are the problems around the prismatic battery? What you can see. One, you can look at the internal weldings. Second, you can look at the tab inspection, the current collector inspection. Third, you can look at the overhang measurements, which you see here. Fourth, housing defects, voids, delamination, electrode damages. So this can be seen without the battery being exposed. The battery can be reused again after X-ray. In a little more detail, welding effects means bumps, pores, internal bubbles, and so on, which will increase the ohmic resistance of a battery. This is in case of a prismatic cell. The same can be done for a pouch cell also. Overhang measurements in a pouch cell. I'm happy that Rahul mentioned pouch cell is going to be a kind of future. It's very easy to check a pouch cell because it does not have a very thick covering. So you can really do a nice X-ray and look deep inside the pouch cell. This is an example of a prismatic cell. You can see the electrode windings can be different. They can bend, they can touch one another. You can look at the metal contaminants, you can look at cracks, all while the part is actually in shape. So you can really figure out what's going on inside. If you give more time, you can really delve deep inside the cells. For example, this scan is done for about 1 hour at 8 micron resolution. Imagine you can section deep inside a battery at a resolution of 8 microns. You can look at the anode, cathode, not the separator really, but you can look at anode, cathode. Welding, there was a talk about the leak testing from Mr. Franco. You can see here the welding of the batteries. You can look at the porosity. You can look at if the welding is good or there are more porous components which can compromise the battery's safety. Not one battery, you can check multiple batteries and look for overhang. This is again a pouch or a prismatic cell where you can find the long overhangs are there, which can lead to safety issues and short circuiting. So this pouch cells from consumer electronics are very, very easy to check, including the electronics or the connector components which are there. Stack alignment, again, Rahul spoke about it. So you can really look at from 2 directions, how is the stack aligned, good or bad. Okay, this was about the cell. Now coming to module, yeah, you can look at the modules also. You can look for similar things, but you are looking at module as a set of cells. So overhang, housing, welding, bus bar, and metal contamination and so on. So this equipment is available at our offices in Bangalore. Please do come talk to us. Similar requirement of overhang and tab inspection. You have the macro welding or the bus bar welding, which is shown here. Welding defects in pouch cells. As I told you, pouch is really easy and nice to check. And we can look at even the electronics and so on. As we can see here, the thickness of foil was really spoken about in detail by Rahul. The thickness of the foil can be easily measured without destructing the cell. Electronic components, because I see a lot of battery packs, where the electronics is deep inside. If something is not working, you do not know whether the connector is good, bad, ugly. You can view the connectors, you can look at the pins and see whether they are mating or not mating. As I was showing you, now if I summarize, you have 3D X-ray topics in which you can do a non-destructive testing of cells, 3-dimensional or 4-dimensional, and no real microscopic information. That means you can do it about in the resolution of 8 to 10 microns. If you want a still higher resolution, you go down to light microscopy, where you can measure a large area, fully automated, but it is 2-dimensional. SAM is where you can look at the crystallographic information, little bit of chemistry information, SEA layer, and so on. Inner workings can be seen, but that is a destructive methodology. Again, an example of how you can look at electronic PCBs, components, and connectors and battery in an X-ray machine. In principle, you can put something from 5 millimeters to 600 millimeters, even battery packs. Large blade battery packs can be installed inside the machine and they can be scanned. Just a summary overview, you have different methods, different requirements, and everywhere X-ray equipments can be used to check the condition, quality of battery production or incoming battery. If you have batteries incoming, if you're buying large batteries from different areas, you want to compare vendors, are they giving you what they promised? Talk to us, we can give you a solution. This is a competence center in Bangalore. Walk in, we have most of the equipments, what I've demonstrated is available here, and we could work. Do I have a few minutes, Priyakshi, that I have a few more slides into deep dive?
Yes, please go ahead, Manoj.
Okay. So as I mentioned, we have these equipments available. So you can walk in with your batteries and get your batteries tested. Now I will, a short view of the company. Okay, we are a 175-year-old company in India for a long time. We are into ophthalmology. Our idea is to, make things visible. Okay. Now, this is our office with a competence center, and we are about 22 years in India. We have factories for CMMs and other components. And I will show you a short video of how you can go deep inside, because people have come to us after checking the cells. They have told us the resolution of 8-10 microns is not good enough. We want something more. Okay, we said we will give you something more. So this is a video of what can be something more. If you want to look into the apple seed, yes, you can use an X-ray CT to look into the apple seed. But actually, if you want to go and look deep inside the seed, you want to look at if the quality of the seed is good or bad without cutting it, then we have another variety of CT, which is also used for battery research. So here, I will not get into the technology, but I'll show you what can be done with it. So here we have, again, an X-ray, but we also have optics inside, with which we can go deep inside the seed, look at if it is qualifiable. We can go deep inside, electronics, battery, additive topics. It's very much useful with battery. You can see this video. This is actually a real image of what is imaged. You can look at the layers, the different battery layers in all its glory by coloring them, looking at different chemistries or different colors. Okay, now I'll show you how this can be used. What is the purpose of this machine? This machine now can be used for coin cells, prismatic pouch cells, to reveal a lot of things. As you can see here, this is a typical, cell, which was a prismatic pouch cell, which was used inside a Nokia, if you guys remember. So now this is put inside a machine, which is an X-ray machine, but with a higher resolution. You can see either the full view of it with a connector. You can go deep inside to look at the layers. You can go still deep inside at 0.4x and look for the anode cathode separator and the foils. If you want to go up to 40x and even look at what is going on inside while it is getting charged and discharged, that can be done. This is actually superlative level of technology. This is also going to be available at our office in Bangalore. So do visit us. And another example, it's an 18650 battery, which has been measured for 5 hours. And then you can get a complete 3D CAD model like the one what you see here with the video, what you can see here. You can get a complete model of the battery. Not a few layers, but a complete model. You can virtually go inside, look what has gone wrong or what is right. And you can color different materials differently. You can look at the porosity. You can look at the compacting, what has happened during the slurry and the coating and on the calendaring processes. You can look at the effectiveness of calendaring. So this is an amazing tool This is not virtual. This is virtual, but this is from the data of an 18650 battery. So this is not animation. Please note. This is again what we can do. These are all not animations. These are real data measured. This was what I was explaining for a pouch cell. You can even look at the electrolyte bubbles because we have such kind of high resolutions. This is all done without destructing the battery. The battery can be put back into production. That's the level of technology what is available. Summarizing, a lot of X-ray solutions are available inline, outline, and for research. And it is very complex. We have now covered only the packaging and the bulk defects. We still can look at porosity, particle size, ACI layer, and raw material analysis, which we can do at a later stage. Thank you so much for listening to me, and thank you, EV Reporter, for the opportunity.
Thank you, Manoj. It was a very insightful presentation, and not just informative, it was visually very appealing. So very nice. Okay, I'll quickly launch another poll based on Manoj's presentation and the information he presented. I would request all the audience members to please share their opinion on it. And once we're done with the poll, we will move on to the question and answer round quickly. In the meanwhile, I can see that a lot of Q&A has already been answered in the box by Preetesh, Rahul, and Manoj. So thank you so much for that. It saves a lot of time. And I can see some of the questions have sort of been covered during the presentations as well. So if anybody has any questions regarding that, or they want to revisit, there will be an opportunity. We will be putting up the video of this recording on our YouTube channel within this week, and the attendees will receive an email when that is done. So those aspects of the lithium-ion cell manufacturing and supply chain can be revisited from there. I would request the remaining audience members to please mark their responses on the poll quickly, so that we can move on to the Q&A session. Let me just close the poll, and we will start with the Q&A session now. My first question is to Mr. Franco. Franco, are you there?
Yeah, I'm here.
Okay, just give me one second. I'm just adjusting the view. Okay, right. So my first question is to you. You presented an automatic machine for leak testing with electrolyte tracing of coin battery cells. So the question is, can a similar approach be proposed for different other types of cells as well?
Yes, of course. It's clear that we are talking of the same method that must be tailored on different type of cell. So the method can work for prismatic, for cylindrical, and with some different tooling even for pouch. Pouch is clearly a more critical type of cell, because we have seen that the common element for this kind of test is the need of vacuum chamber, and for sure a pouch cell are quite sensitive to vacuum, so specific toolings must be used in case of pouch. But I would say that for all of this type of cell it can be applied. It's clear that based on the size of the cell, the type of electrolyte to be traced, the type also of the cell, so that means if it is prismatic or cylindrical or pouch, the sequence must be readapted, and also the cycle time, so as a consequence, must be recalculated, including the number of cells that must be placed inside the vacuum chamber to optimize the process.
Mm-hmm. Okay, understood. And
in any case, I would say for any specific request, enter in contact with our colleagues because depending on the type of the cell must be done a specific evaluation.
Okay.
Okay.
I would also
Thanks.
request Hanish to please share the contact details on chat if somebody missed it during the session. If Manoj, you could also share the contact details on the chat.
Sure, Priyakshi.
Yeah, I'll do. Yeah.
Sure, Priyaksha.
Rahul and Preetesh, it's similar request to you as well. If somebody wants to get in touch after the event, they should have a go-to email address or a phone number. Okay.
Sure.
Thank you. And Franco, one more question. You also mentioned about cell selection and grading. So what are the parameters on which this cell selection and grading can be done and or is usually done?
Look, I would say that part of this is, I would say, also something that will depend a lot on the use of the cell. But I would say that generally speaking, especially when talking about the use of battery cells for automotive industry, the main task for grading is to have the possibility to assemble cells in the modules which are as much as possible homogeneous from the point of view of their electrical parameters. So that means that considering that you have the cell connected in series and in parallel in the module and the pack, as a matter of fact, the behavior of the complete pack will depend on the worth of the cell. Okay, so that means that the main task of the BMS of the battery management system is in some way to keep balance the behavior of the different cells. So it's clear that what you expect to have is a cell which are as much as possible homogeneous when you make the assembly, and also if possible to predict what will be their behavior in future. So open circuit voltage and ACIR are two parameters, especially ACIR at least two different level of frequency are parameters which are frequently used. Of course, difficult to say if it is better to work with this or also DCIR or other kind of test. Must be evaluated case by case on the type of cell and the chemistry, the size, and so on, and also the use of the cell.
Okay, understood. Rahul, there was one question for you on chat. I'm not sure whether you had a chance to see it. So the question was, the recent fire incident in two-wheelers that we saw, was that primarily due to cell chemistry?
See, thermal runaway, to be frank, all these fires, if you see Ola is NCA, others you see, I don't want to name the names, but they're all NMC. And NMC catching fire frequently is not a very common scenario. It happens very rarely, but they do catch fire. Even the biggest of the Teslas are catching fire, who has been there for over a decade. So battery failures, it's not that something that does not happen in petrol diesel vehicles. Even they catch fire. Even the CNG, whenever you go to a CNG station, you are told to come out of your car because there can be a small chance the cylinder can burst. So these are all some of the things that we are supposed to be frank, we are supposed to reduce the error rate, but they will be there. That's a law of all these things. And even LFP batteries are catching fire. You might have heard of the buses and the Tata car and all that, but LFP internally short circuiting on its own is not going to catch fire. External short circuit, see, even the biggest of the buildings are catching fire, water batteries. So external short circuit cannot cannot spare anybody. Internally, yes, NMC and generally NCA, they have the high tendency of catching fire because the thermal runaway, when it achieves thermal runaway, is much lesser compared to LFP. LFP is upwards of 200, NMC is close to 200, NCA is much below 200. So that is when they start releasing and all, and the SCI layer decomposition happens much before 100 degrees and all. And then all this short circuit happens. It's a quick thing that happens. But yes, all these things are not LFP.
Okay.
So
Understood.
these are the basic things.
Okay. So we're saying that the cell chemistry, definitely there is a, you can
Definitely,
identify
definitely.
which,
See, you
which,
want something to be lighter and compact, and obviously you're compromising on the safety. There's a limit. See, from lead acid coming all the way, this itself is an achievement. It's too much to ask that you want a battery which is 300 plus watt-hour per kg, which has unlimited cycle life, which charges in minutes and all. You cannot ask. You can ask, but you will not get it. You can keep trying. Like
right.
Preetesh was telling, sodium sulfur is coming. Yes, that is already there. Some of my friends are already working on it. But what is the challenges? You can try all this fast charging that uses lithium metal as anode, by the way. So you can fast charge and all, but dendrite formation. So anybody can tell you why lithium sulfur, it is the much lighter. It starts from 300. Lithium-ion batteries maxes out at 300, something like that. This is pretty much starts from 300. It can go 600 also, not a problem. Cycle life just very bad. Nobody's able to cross 100 or 200. Would you buy a battery which has 200 cycle life? Second thing, dendrite formation on the Li metal anode, huge. These are the two problems that people are working on. Whoever solves, they will win the race. But solving that is also, see, thousands of papers come out. People keep asking me, Rahul, what is a zinc, copper, and all these batteries and all. See, any two metals, when they have the difference, you put them together, obviously there's a potential difference. There'll be, a voltage that can hold the energy. That is always possible. That does not mean that you can just make it. 31 years and lithium-ion is still standing. It's here to stay. It's not going out anywhere. And people keep asking me, what is this sodium ion? All these big companies are looking at. It is coming, but definitely not for EV. Sodium ion's energy density gravimetric is much lesser than LFP. LFP is struggling to enter the EV market, especially two-wheeler. Sodium ion definitely not happening. And the answer lies in the periodic table. You can see lithium is here, sodium is below that. So molecules are bigger. There's your answer. Look at the periodic table. So let's be realistic here and let's talk about the real things. LFP and NMC. These are the two choices that we have. If you can spare some extra cash for thermal management, go for NCA. It will definitely make your batteries light. So these are the three things. In fact, Tesla is moving away from NCA. They used to completely use NCA, and even NMC. All the Tesla batteries you might be hearing, they're catching fire in in different places. The energy storage, they use NMC. They were anti-LFP, but end of the day they are surrendering to LFP. Why? Because they were not able to make. Panasonic does not have the patent to make LFP. That's why they were using something that they had access to. 2023, the patent opens up. The West, Americans, everybody's going to start. SK Innovation is planning, and Tesla also has plans. So it's the patent that is holding on. And patents don't really apply in China. Let's be realistic here. So you cannot sue the Chinese in China. It's very simple. And they have the supply chain. They have the power to manage own the mines and, operate the mines. So they are having that edge. So even if someone wants to make LFP in India, they need to take care of all these patents and take the rightful information, and only then they need to enter. But good thing is that LFP has been proven and all that. Even NMC is highly patented. See, anything you want to do, you have to take the rights and all the ownership and the permission from the rightful owners. This is the way going forward. Coming back to your question, yes, it's all NMC. It's all oxide batteries, which have the tendency to catch fire. Sometimes I don't blame the chemistry also. It's the pack, the way it is made. If you see how battery packs are generally made, people want to make it as compact as possible. They keep the spacing and all low. So the good thing, I think one of them was asking about EAS 156 amendment, the new one. So that one is more to do with government says you will have to maintain decent amount of space between the cells and all those, and you should have the thermal propagation. If a cell catches fire, which in case it happens also, how are you preventing the other cells from catching fire? These are all some of the wonderful steps that the government of India is doing. But how it is being implemented and what is the cost implication? Batteries are going to get expensive with this. Vehicles are going to get expensive. Are the customers ready to accept this new price? That is going to be a big challenge. So that is where the industry, in fact, talks are happening with the ministry and all. So a lot of up and down drafts are being spoken and all that. But it's a very good initiative as of today.
Right.
Taking safety into the thing.
Definitely, it's the need of the hour. But the time that they have given to move from the current standard to the updated standard might not be, enough. Given
See, it is the ask. You can ask for the moon. Now industry has to come back. So industry is giving back a good reply that, okay, we adhere to so and so by so and so date. So there's the associations and people all active, all the companies, everybody is in fact welcome to be part of this and propose to government. it's something that government is open to. See, obviously the government has to listen to these industries when they're imposing something. They cannot just, we are the largest democracy. So that all that is taken care of. We are seeing very good response from the government, but government is saying, what about this between gap, which the safety is being risked? These are human lives we're talking about. So government is taking this little bit strictly. Had it been something else, government have given extension after extension. You might have seen the fast tag. It was, I think, 2020 people were talking, and it took almost 2 years to implement. But safety, when we're talking human lives, then government is like little pushy. They're like, you will have to push this a little bit harder. So that's the reality. What's happening here.
Okay. Preetesh, are you there?
Yes, Preetesh.
Preetesh, there is a question for you. Your thoughts on how easy or difficult will it be to achieve a 60% local value addition for cell manufacturers within 5 years?
Yeah, so
that's too easy, Priyakshi, by the way. I know all these companies who many vendors are being developed. Sorry to interrupt, Pritesh. So graphite already, many companies have already starting. It's just the mines that you need to further, purify them. The purity has to be increased and a little bit engineering, graphite. And when you want to make LFP, that's very, very easy. You basically need lithium carbonate, iron oxide, and phosphoric acid. Yes, we don't have lithium, that's true. But iron oxide, cheaply and abundantly available. And phosphoric acid, already the fertilizer industry is using it. And coming to the separator, it's just plastic, polypropylene, polyethylene. Come on, how hard can it be? And Electrolyte, yes, the LiPF6, the base needs lithium hydroxide, something is used, and that again needs to be imported. So these two lithium barriers are there, or else you can make the perfect LFP battery in a country. Copper foil, yes, again, sorry, I'm taking a little longer for this. Yeah, copper foil, it's an electrode deposited. It's expensive to make. Some of the Japanese companies are giving solutions and all. But if someone has the vision to make the expensive, put in the difficult capex, heavy capex, they will definitely reap benefits. And then copper, then the aluminum foil, that's pretty much, you need to maintain 10 to 12 microns. You got it covered. 100% is no difficulty. And when you say localization, does not mean you need to mine in India. The subsequent cathode and the anode, the electrolyte and all, that can be made in India. So someone else going backward, suppose, LFP can be made in India, iron phosphate can be made in India, lithium carbonate can be imported, say, from Argentina or something like that. So if for the cell people, 100% is possible. For the raw material supplier supplying to the raw material supplier of the cell, they might have this issue. So localization, we need to ask, how deep are we talking? Are we talking mine to the vehicle? That is the complete end chain that generally exists. Back to you, Pritesh. Sorry. Yeah.
Yeah, I think, Rahul, you covered it all. But I just would like to mention that, Priyakshi, the definitions are made in a way that it is easier to meet this 60% because it's not localization, it's value add, in which the margins of the companies are also included. And by the way, those are very high at this point in time. So when you divide this entire 100%, the margins and the anode, cathode, electrolyte, everything's there. So in India, if you look at, I think anode, cathode, electrolyte, and separator has to be localized to achieve the 60% value add, including the. So next 2 years, 25% is not a challenge, but next 5 years, 60% value add is very much possible because anode, you can, there are already suppliers, like there are 2-3 suppliers from where you can buy the anodes. Obviously, there has to be some upgradation for them, but they can do it well. And then there are possibility of cathode manufacturers also coming to India when there is a volume. So very much possible. And the way the government is deciding, and also kind of tracking this on weekly or monthly basis, I think they are going to make it.
Okay, thank you, Preetesh. Thank you. So there are a couple of questions on AI's 156 standard. So I think that will take another if we.
I think we should do a complete session on that where we debunk everything point to point.
It requires, yes. I don't think we can.
We can do that. We need to do a separate session for that. Yeah. But all in all, it's a very good, very pushy, very overall with a very good, well thoughtful, thought kind of process. But it takes time, and it's going to allow only serious players to be, and some of the small people who were compromising on the quality, cutting corners, they are all going to fade away. So only serious players will exist. So all the year by year, the battery packers were increasing. Now probably after this, some of them will come out, or they might focus on non-EV applications such as solar and some home UPS or some kind of ESS applications.
Okay. Manoj, there is a question on calculating the state of health. Is that something that Zeiss would cater to?
No.
So you are
Actually,
so,
I have done one project in Manoj. I'll tell you, state of health with aging, the SOH value changes, and when that happens, you would want to scan the cell and see how it has disintegrated.
That is
So
possible.
that is something I've done with Manoj. So I was pointing out.
Yeah, that
A
can
new
be.
cell will have a different structure,
Yeah.
and at EOL, which is where the SOH has come down to 70, so the structure will be slightly different.
Yeah,
That
the
is something
SOH cannot be calculated, but the effects which lead to SOH can be monitored and can be seen very, very nicely in our equipments. Which
in fact, someone was asking how to calculate. So SOH is basically the energy storing capacity as of today divided by energy storing capacity of the cell when it was brand new into 100 will give you the SOH percentage. So a new cell will be 100. After cycling few hundreds of cycle, it would probably come down to say 95, 97, depending on chemistry. Yeah.
Okay. Understood. I would also request all the panel members to have a look at the open questions. Many of them we have just covered. AIS 156, we will definitely try to plan something in the coming month or so. I think we have pretty much covered all the questions that are being asked in the Q&A. So, and also we are at 5:30. Rahul, there is a request for your phone number. If you could.
Yeah, I'm just putting, sorry.
Shared it earlier. So I think with this, we will wrap up the session. Thank you so much to all the experts who joined us today and actually making such good, insightful presentations.
I've sent my details.
Yeah, it's available on chat. In fact, all the presenters have shared their details on chat. Hanish, I'm not sure whether you've shared.
Yeah, I've shared. Yeah,
you've shared. Okay. Yeah. All right. Thank you so much. So thank you, everyone. Thank you for the audience, to the audience members also for making this a productive and interactive session. And we will come back to you with more such interesting webinars. One good takeaway for me personally from this event was that we need to cover AIS 156 in a lot of detail. A lot of people in the industry will be benefited by that. So we will take that into account. And once we close the session, there will be a small survey, just one question survey, and I would request all the audience members to please respond to it. Thank you, gentlemen, for all your time. Have a good rest of the day. Thanks.
Thank you, everyone.
Thank you, everybody.